Hello. So yeah, I'm going to sort of talk about a bunch of research that a group at the UW has been working on for the last year. And we've been doing a bunch of stuff with Node that probably isn't what it's really meant for. And one of the sort of things that you can have in the back of your head about what the sort of point at the end of all of this is this map, which is looking at the top 10,000 websites. Where are their servers? Where are the points of presence for all of these CDNs? And you could maybe think, okay, I can probably make a map that looks sort of like this by pinging all of these and geolocating them. But the interesting thing is that for a lot of these websites, like a quarter to a third of them, they're not like one server, right? They've got a CDN. They've got different servers in a lot of different countries. And so figuring out where all of those servers are suddenly is a thing that's a little bit harder. The CDNs don't tell you this because that's their secret magic juice. So part of what we get to do is go and figure it out for ourselves. So the project is called Measuring the Internet Stars. And one of the things that we went into this with is how much of this can we figure out from one machine that I control at the university. You probably have dealt with things called distributed systems and know that they're a huge pain. And that's true. But when you're thinking about distributed systems and you're thinking about, well, that server might crash, and so we need to be fault tolerant, that's different from when the academic research group is thinking about distributed servers or distributed systems, which is half of them are down at any given time, and another half of the ones that are up don't have SSH working. It's Planet Lab is a thing that exists and sort of has been limping along, and it's just they ask different universities around the world to have servers, and they're administered by some grad student who maybe restarts it when they get enough emails. And so we're going to try and not do that. So once I'm limited to my machine, how am I supposed to figure out, does Google have servers in Taiwan, and where are they? This starts to be a little bit harder, because if I just go to Google, I'm not getting the ones in Taiwan. So we use a couple techniques. One of them is DNS. DNS is the domain name system. And this is how we do resolution. So when I type in CascadiaJS.com, it gives me some numbers back, which is the IP address. And the way that system works, with a great graphic from Wikipedia, is my computer is going to ask a DNS resolver to do that lookup for me. So I say, hey, who's CascadiaJS? And it's going to give me back the number. And if it doesn't know, it's going to do this sort of multi-tiered lookup. It's going to first go to one of the DNS root servers. There's a bunch of these around the world. And those servers know who owns .com and who owns .org. So then it'll go over to one of those servers and say who owns CascadiaJS. And they'll say, well, that's registered with GoDaddy or one of these registrars. And then it goes to their servers who actually know which server is that www.cascadiajs.com. And one of the interesting things is that there's a bunch of these things that you can ask that will do this work for you. So you probably get one when you just plug in your computer with DHCP. It comes with whatever your local ISP's server is. But you may have explicitly set some when you're not happy with that. 8.8.8.8 is the Google one. Maybe that rings a bell to some of you. There's others. There's OpenDNS has some. Comcast has its ones that you may use if you haven't changed it. But you can go out and just sort of say, well, how many are there? And there's roughly 8 million of them. And you do this by just sort of asking all 4 billion IP addresses to resolve things for you. And the 8 million of them get back to you. And those 8 million are in 5,000 different ISPs. And there's roughly 170 countries that have at least 20 of them. And that's pretty cool, because once we get 15 or 20, we can start to not just say, I trust this server to tell me things, but rather I can do some statistical significance things and be well, everyone's telling me the same thing, so that's a good sign. So we're gonna start scanning both to find all of these DNS resolvers that will give us stuff, and then also asking them to resolve domains for us to figure out what do they see this domain being. So who do they think Google is? Who do they think any of these other popular websites are? I guess it's worth pointing out there's a lot of people who say having these things be open is a bad thing. There are security risks here in terms of DDoS amplification attacks that happen around DNS. So when you do this, you will get complaints. So this is like, don't do this at home, or you'll get angry people being like, you're making the problem worse. But all the code's online. The other thing that we use is HTTP, so we're going to try and resolve favicons and make sure that some server is actually the server we think it is. There's actually like on the order of 100 million IPs out of the 4 billion total space of IPs that are running web servers. So you've got like 2%, something like that, of all IPs are actually running web servers, which is pretty cool. And then there's this like much smaller number of HTTP proxies that will give you web pages for any page instead of just for like whatever it is that there are servers for. So we're gonna try a bunch of this indirection. It turns out it's basically as much trouble as dealing with a distributed system in the first place, but like at least there's only one server that I have to SSH into. Cool. So I'm gonna we've got this code that's gonna run, it's gonna resolve, it's gonna like send a bunch of packets, get some packets back. Now we have to understand what that means, and we have to deal with a bunch of data. So I'm going to spend a little bit of time to talk about IPs, and maybe you'll learn a little bit more than you ever really wanted to about IPs in the process. So this is an IP. This is IPv4. This is an address. We've all seen these. So an IPv4 address is 4 chunks, altogether 32 bits, 1 integer. IPv6s are just sort of longer and uglier, but followed the same sort of mental model. Back when we had sort of limitless IP addresses, we talked about IP spaces sort of in a few different ways. They would give out /8s or class A address spaces, which is just that first number, to big organizations. So Apple is 17.something.something.something, and MIT has 18.something.something.something. And then we realized that we didn't actually have an infinite number of these. We had like 256 of them. So that wasn't going to scale. So then we started giving out class B and class C. So like you've only got the first 2 defined or the first 3. So you get 256 addresses. And then you come forward a few more years, and we realize this isn't going to work because someone wants more than the 256 addresses, but you don't want to give them like 65,000 addresses. So we can't just do class A, B, and C. And so we got this thing called CIDR, where you specify in bits how many bits are the prefix and how many are the amount that you're allowed to control. So you've seen this probably as like your network mask or your subnet mask. There's a lot of words for this. Speaking of words, there's a lot of jargon. Sorry. But this last number is sort of specifying how much is owned by this organization versus how much is like it can give to its individual computers. So the 24 means the first 3 octets are part of this like group of IPs, and we're talking about 256. But now I can have a /20 for a little bit more, or a /27 for a little bit less, and we have that ability to control that. And so that's how we actually allocate IPs today. And in fact, a bunch of these like original like class A addresses, they've asked, well, you need to give back some of those if you're not using them. And so now you sort of have subdelegation. So what do we do with IPs? We've got IPs. We want to know where these IPs are. You've probably used MaxMind, which is a geolocation table. There's a couple of these, right? So I've got an IP. I want to know where in the world it is. I'm going to go to some web service, and it'll tell me. This is great, except if I'm like writing a paper about it, and I need to explain why I know that like these servers are in this place, I don't want to just point to sort of, well, I got told that. So we have to dig a little bit deeper and figure out how they're doing it and how we can do the same thing. There's also there's 2 issues that we've run into. One is a lot of times you have an IP that's actually in multiple places. So this is Anycast. A bunch of CDNs use this. And this isn't a thing that you will get from any of these databases. It's telling you, well, this IP actually is both in the US and in Europe. And you go, oh no. And also for a bunch of like core infrastructure routers, that's not what this is designed for, and you just won't get any result. So this works great for users who are visiting a website. It's not going to work if you're trying to like figure out where the core internet routers are. So how do IPs, like how do I know where they are? Like someone owns these. There are some computers. Presumably there's something out there that is like the definitive thing. It turns out that the technical like incarnation of this world map of who owns what is BGP. So BGP is how computers are going to route to each other, right? So some organization is going to say, I own these IPs, you should send me traffic that is destined to them, and other people will do that, and that makes the internet work. And a lot of organizations actually are willing to publish their table of what they see around the world in BGP, and it looks something like this, which is just complete, random numbers. But what's important is that first column is one of these subnets. So that first line is saying 223.255.247.anything. The next hop goes to some IP. You should sort of send it over there. And then that long string of numbers on the right is the different organization IDs that it's going to pass through, with the final one being the guy who owns it. So we've got this nice mapping now of some network being owned by some number. That number is called the autonomous system number. It's the official registration that Comcast or any of these ISPs have, right? So they've got some number. That number is registered in some country, and then it's registered with ICANN, the international organization that registers these things. So we can actually say, well, okay, this set of IPs was at this time being routed to this ISP in this country. And that gives us a good first pass at, okay, what country should we expect these IPs to be in? The problem is this table is pretty big. It's roughly 2 gigs. And there's like 21 million lines. And so we have to deal with it. The other thing that we care about is when I'm looking for a specific IP in this 2 gig table of mapping, there's going to be a lot of lines that match. Like for instance, that example of 8.8.8.8 I gave, that's been subdelegated to Google. So Google owns that little small 8.8.8. whatever part, but that's within this larger 8 dot things that was originally assigned to level 3. Or it was originally assigned to someone who sold it to level 3, but it's controlled by level 3 right now. And so I have to find the more specific one. So I may have to there may be other things that match that I then don't use. And so I have to go through a few different entries to get to the one that I care about. But this seems doable. So let's build a table in JavaScript that can do these lookups. We'd like it to be able to do that pretty quickly because we've got a lot of IPs to get through. Hopefully we'd like to get this to be pretty quick as well. Seems plausible. So, step 1, how are we going to read that data? If I just call read file, that's not going to work. And luckily, I think we all know this. Streams are the best. We can make a stream. We can pipe through line by line because it's all just line by line. We can run some regex and pull out the things we care about, and we're good to go. Streams are great. And if you want more streams, I highly recommend Stream Adventure. It's a great intro from Substack on streams. Okay, so we've got data in. Now we need to figure out how we're representing this data. And this is the part that was pretty counterintuitive to me. So I showed you that tree. And our initial, let's get this as a map was, okay, so we've got our general prefix, and then we're going to put the more specific prefixes within it. And this seems fine. We've got a key and we've got a little object. And this works pretty well. The final JSON.stringify of this whole thing was 30 megs. It took 2 minutes to push through it, which isn't too bad. And it was super fast to do the lookup. And one thing that was annoying was every time you loaded that 30 meg thing back into Node, it took a second and a bit, which wasn't great. And also this table was 30 megs, which was pretty big. Because the Maxmind database I can download is 2 megs. So I was not happy about that. So one thing that we realized was a lot of the effort here is going into making these objects, and you don't necessarily need those. So we tried to flatten it. So we're just going to have all of these just be in one map, like this. And suddenly your table goes down to 13 megs, which sort of makes sense, right? We've gotten rid of, like, this is less text, less letters. But also your build time goes down to like 20 seconds, and your load time goes down to like half a second. But your lookup time goes up a little bit because you sort of have to like start doing some more lookups in your big table that takes some time. And then the only other thing that was slow here was that 8.0.0.0 to actually calculate all of these prefixes as we're starting with our specific IP and like saying, well, okay, so is there one that's /31? Is there one that's /30? Is there one that's /29? So you have to keep recalculating that number. And that ended up being like you go into a number, you do your little math thing, take it back into your IP address format, you go back to the number. And if you just leave it all in numbers, you can make your lookup time be fast again, but it looks ugly. But that's fine. Cool. So we've got like a thing that's fun, and then this suddenly is like, I don't know, one of those like little algorithmic puzzles that people just get really excited about. And so like I've had people in the lab just spend a bunch of time finding all of the duplication in it and like writing the little thing that makes it smaller. And we've gotten it down to 2 megs, or if you are sending it over the wire, like with gzip, it's down to like 400K for the whole table. Because there's all of these like crazy math things that you can do with this at this point, and you're like, this is like a problem that I can like compress in like fun ways. So we've got IPs figured out to some extent. So let's talk about connections. We're making a lot of connections. And like, we've got this core, which is we're doing a ton of connections. We're looking for the Alexa top 10,000 domains. And we're looking at them against 8 million open servers. And so you can do the math, but that's a lot of billions of IP like datagrams that we're sending out, these DNS queries and responses. When we first got like a server to do this, we accidentally broke the UW's internet because we were sending too much, and their intrusion detection firewall fell over. So since then, we've gotten our own like dedicated link to the Westin downtown, which is the big internet exchange point in Seattle, and so we're not going to take down the UW's connection again, which is pretty cool. But for that like core piece of sending a ton of packets, we don't want to maintain any state, and so that is done in like this optimized piece of C called ZMap that already existed. But we're processing the roughly 400 gigs of response that we get each week with a node stream pipeline. And there's not like that much beyond streams that you need to just do this reasonably. Once you get up to enough hundreds of gigs, you probably are going to realize that you want to use multiple cores, and you're going to split it into like a few different node processes that each take a slice. But other than that, you're good. And so it's going to look something like I'm gonna map my incoming stuff. This is what we're using for favicons, which isn't in that tight loop. So we're going to fetch favicons from a bunch of all of the IPs that we found as potentially IPs that are servers. And we're just going to map it through something that does the request. One thing that it didn't give us is the ability to choose sort of our concurrency level. You've got a high watermark in this concept of streams of sort of how much stuff is flowing through your stream at a given time. But we ended up with the need for more control over that. So we ended up making a map concurrent where we could explicitly set how many things are going at a given time. And that ends up being, 5 lines. And so this is like, we're going to fit into this fun NPM world of doing one thing well. And we're going to end up with a bunch of these little NPM modules that end up making this sort of thing not only reasonably easy to understand, but also it's a really cool thing for undergraduates who come in for a few months, or interns who come in, are able to come in, own some module, make it work, and then they've got that thing to like show off later. So we found that pretty cool. The other thing that we use everywhere is a thing called progress bar stream, which makes little progress bars show up whenever we do things, so that we can tell, is this like a thing that's going to take a minute, or a thing that's going to take an hour, or a thing that's going to take 10 hours. And between those things, like, you're good to go. You can like, I can talk to you about like memory exhaustion, which happens if you do things wrong. Like you make a map that is going to like grow, but you see that by running top and being like, oh yeah, node's about to run out of memory. And other than that, use some streams. There's a thing with all the data. If you want to play with data yourself, we've got both the original data and then the like extracted and aggregated down to like sane amounts of data on satellite.cs.washington.edu. And you're welcome to play with the IP stuff or like some of these fun progress bar things. So thank you.